All right. Hello, guys. This will be our last lecture before the first midterm. So this is all the midterm will cover. Midterm one will cover. And we're dealing with 13.6, the directional derivatives and the gradient vector. Okay. So first of all, let us sort of introduce what we're going to do now. In the previous chapter, we have dipping really deep on the definitions of partial differentiations. Specifically, it is in the x direction and y direction. So in this chapter section, we're going to introduce you how to evaluate the derivative in different directions. But it turns out that it will be sufficient to only compute the direction in x and y, which we will see soon enough. Right. So first of all, let us define this notion. So the directional vector is given by the following definition. Given a function f, in this case, a two-variable function, and as always, it generalizes to multi-variable functions, the directional derivative of this function at a point AB in the direction of a unit vector, u, in this case, I denote it by u1 and u2, is defined to be this quantity. And we use du here and fav here, which is defined to be the limit of the difference in the numerator between f of a plus hu, b plus hu2, minus f of ab divided by h. So you can see that this definition is actually quite natural. It is simply saying that if I move slightly along the direction u1, u2, what is the change of that direction? And we can see that actually this is a generalization of the usual partial differentiation. We see that the usual partial differentiation in x is simply in the direction of 1, 0, right? In the x direction. And for y, it is simply the y direction, 0, 1. So this kind of definition generalizes that what we can do for partial differentiations in different directions. And the reason that we use the unit vector is to control the size of the differentiation, which we will see soon why that is the case. But just remember that if you're computing a directional differentiation, then you always have, first of all, the function, second of all, a unit vector, and third of all, a point. Okay? All right, now let us do some example first. So here I want you guys to compute the the directional differentiation of f at the point 3, 1 along the direction u, where u is given to be this unit vector, minus 1 over root 5 and 2 over root 5, where the function is given to be x squared plus 1. And so directly by definition, you have that we plug in f of, which is 3, 1 plus hu, right? And that gives us 3 minus h over root 5 squared plus 1 plus 2h over root 5, where this is simply f of 3, 1. And then by definition, actually by foiling, you get 3 squared minus 2 times 3, which is 6 times h over root 5. And you have a square term here, a square over 5. So we can see that as 3 squared and 1 cancels out, and the remaining terms is simply this 3 guys. Dividing by h, you get 6 minus 6 over root 5, h over 5, and 2 over root 5. So by taking h to 0, simply get 4 over root 5. And that is the rate of change of this function f at the direction u. Okay, so one can say that in some sense, the function is actually increasing along that direction. It is going this way, right? Okay, and as usual, we want to derive a proper formula for the directional differentiation. And it turns out there is one instead of computing the limit all the time. So first of all, we'll introduce this notation, which is called a gradient. Gradient is defined to be, as usual, it can be generalized to general functions, but in this case, let me consider a two-variable function. It is a vector containing the first term being the partial derivative of x, and the second term being the partial derivative of y. So you can imagine if we're dealing with a three-dimensional function, then the third component will simply be the partial derivative of z, and so on and so forth. So this is called a gradient of a vector. We will introduce different notions of this kind of differentiation afterwards, which I think we'll introduce it in chapter 16. It is called curl divergence. But for now, let's focus on this gradient. Okay, and the notation is a upside down triangle. It is also usually called Dale, but as usual, I'll just call it gradient f, right? So what is this notation used for? The following proposition tells us that if f is a differentiable function at the point AB, then we can actually compute its directional differentiation along u by this dot product between the gradient vector and also the direction u, right? So what I'm trying to say is that if you want to compute this directional differentiation, you first have to get the gradient vector, and you simply dot product the gradient vector together with this directional vector. Right. And this is actually really simple to prove. Let us try to do that. So given a one variable function g of h, and we define it as usual to be the f of a plus hu1, b plus hu2. So that's the shift of f along the direction u1, u2. And then by chain rule, by definition, that the directional differentiation of f along u is simply g prime of 0, right? Because you can see that by definition, g prime of 0 is given to be something like this, right? But if you plug in the definition, that is exactly the definition for the directional differentiation of f along u, right? So it's simply g prime 0. But this can be regarded as a composition of functions, right? The first is x of h equals to a plus hu1, and y of h equals to b plus hu2. So by chain rule, we differentiate the first guy first in x, and then we differentiate x by h, which you get u1. And for the second term, you differentiate y first, and then you differentiate the y term by h. So eventually you get fy, in this case, I plug in 0, so everything is 0 here. And so you get fxab u1 and fyab u2. So that is the definition for dot product, right? Simply this, taking dot product with this vector, okay? I want to remark here that due to the fact that this is a vector, usually somebody would do something like this in the del or nabla operator. But just not to make confusion, I usually like to just write this, okay? I think that's also the way in the textbook. So let us confirm this again. The proposition that we're proposing is that the directional differentiation can actually be reconstructed by the two partial derivatives, which is given by gradient of f dot product with u, the directional vector. Okay. And that also kind of recovers the definition of these two guys, right? You see that if this is 1, 0, and this is 1, 0, then this is simply fx differentiation, right? And so on, so forth. All right. So with that powerful tool, let us try to compute the directional differentiation in a more elegant way instead of trying to treat the limit every time. So first of all, I use this exact same example. You see that I'm computing the directional differentiation of f along u at the point 3, 1 with the same function and the same vector as above. So instead of doing a limit, we can simply compute the gradient first, in this case 2xy. And the directional differentiation is simply by plugging 3, 1 into the gradient vector, dot product the directional vector, and that you get the same thing, -4 divided by root 5, right? The second problem generalizes this fact to three variable functions. So I define f of xy to f of xyz to be exy sine z at the point, I want to find a directional differentiation at the point 0, 0 pi over 2 in the direction 1, 3, 2. So first of all, note that this is not a unit vector. So we will always transform that into a unit vector. Whenever we're saying something along a direction, some vector, then you always have to translate that vector back to its unit form. So we have normalized that the vector. To be precise, let us first compute the normalization. You get the length of the vector is actually root 14. So you get 1 over root 14, 3 over root 14, and 2 over root 14. As for the gradient, it is a direct computation. If we differentiate respect to x, then you will get the same thing. Y get the same thing. For z, you have to change the sine z into cosine z, right? And that's all. So now the directional differentiation is again by the formula, the gradient taking dot product with the vector u. And in this case, taking 0, 0 pi over 2 inside this vector, you'll get 1, 1, 0, taking dot product with the corresponding directional vector. And eventually you get 4 over root 15. So again, it is now, this function is increasing in that direction. In particular, this vector is decreasing in that direction, right? Okay. Yeah, I just noticed that I get a signature incorrect here. So let us fix that. It is minus. Let me emphasize that. So, right. Um, so after our discussion on directional differentiation, we see that the gradient vector plays a role in the formula for the directional derivative. And now we investigate more on this gradient thing. It actually plays an important role in the analysis of a multivariable function, as we will see in chapter 14.8, a Lagrange multiplier. But for now, let us first state this proposition in the sense that when f is differentiable, again, I forgot to put an arrow here. I don't know why. Things just happened. So it is a two-variable function, and it is differentiable. And we claim that the directional differentiation is maximized whenever u is parallel to the gradient. And this is not a really good notation because I recall that in the vector section, I state the parallel in the sense of you can be either opposite or actually parallel, right? So I want to emphasize here that by parallel, I mean they actually share the same direction instead of you can have this and this direction. So basically, I'm saying that u must be a constant multiple of the gradient and a must be positive, okay? And then it is maximized at a direction where the value of this directional differentiation is simply the magnitude of the gradient vector. And similarly, it is minimized at the vector where direction is in the uh, minus of the gradient, and the value is given by minus of the magnitude. Okay. So yeah, actually, all right. Let me write this down. It is better if I write this. It'll be more useful. So basically, I'm just saying this. It is maximized when you are of the same direction with the gradient vector, and you're minimized where you have the same direction with the opposite of the gradient vector. Oh, this is right. I will fix this up. Actually, let me do now. Sorry for this. Okay, I will fix it afterwards. It's a little bit messy now, but yeah, I will definitely fix that afterwards. So it is actually really simple to prove this because by differentiability, we know that you have this formula, right? And by I think we spent a lot of time on this, the dot product actually reduced to the product of the length together with cosine theta, where theta is angle between the two vectors, gradient f and u, right? In particular, the length of this is always 1 because it is a unit vector. So everything reduced to this times this. And theta is affected by u here, right? So we know that when this cosine theta is largest, it is when it is 1, right? And that's when the two vectors actually align, the vector angle is 0. So when theta is 0, that means that u is of this direction. And it's minimized when cosine is minus 1, and that is when the theta is 180. So you have the opposite direction. So basically, this proposition is saying that the rate of change of f is maximized in the gradient direction, and it is minimized at the opposite of the gradient direction. Okay, so in terms of like the landscape of the graph, we can see the steepest slope happens at the direction of the gradient direction. Okay. Okay, so here an example from the textbook. We have an electrical potential adjusting function, basically, given by Vxyz equals to 5x squared minus 3xy plus xyz. So for part A, they want us to find a rate of change of a potential at the 0.345 in the direction of V. So basically, I want to rephrase this. Rate of change is just differentiation, okay? So in this case, we first compute the gradient, which is this guy. There's no big deal in this. It is a strict direct approach of differentiating polynomials. And then we want to normalize this vector. So V is I plus j minus k, which is 1 minus 1 with magnitude root 3. So this is the normalized vector. And then the directional differentiation is simply the dot product between the gradient vector together with the directional vector. And it turns out to be 32 divided by root 5. Okay, so just to know that this is coming from you plugging xyz being 3, 4, 5 into this gradient vector. Okay, right now part B asks which direction does it change most rapidly. So we already know that it changes most rapidly in the direction of the gradient vector and the opposite that gradient vector, right? So we're simply trying to find plus minus of the gradient vector normalized, and then it turns out to be this number, right? So again, this thing comes from here, and then you divide its magnitude, its length. And they ask the maximum rate of change, and we know that it is simply the magnitude of the gradient vector, which is in this case is 2 root 406. And the minimum is obviously minus 2 root 406. This is actually a really, really simple observation, but it's a very useful observation in the sense that we have developed a algorithm called the gradient descent algorithm, in the sense that if you want to find a minimum of a complicated function, it might be a million variable, then a way to do that is always follow the direction along the minus of the gradient. And by going down, you'll get the steepest decreasing, which you can find the minimum in no time. That occurs when the function is too difficult to compute, because we will see in the next section that there is a way to compute the minimum via calculus, but in general, it is not really practical to use that algorithm in your computer. So this gradient descent algorithm is very, very nice to use, and I encourage you guys to look it up. This is one of the nice consequence of this very simple proposition. Okay. Right. So next we want to discuss the um tangent space of the tangent plane of the level surface. So in this case, I fix a function given by f, and that is a three-variable function for R3 to R, and it is differentiable. And I want you guys to find the tangent plane of that function. And turns out that the tangent plane, so let us recall, well, if you want to find a plane, the point is to find a point and also a normal vector, right? So the point is not really important because any point on the tangent on the surface can be some point. And the point is that how do you derive the normal vector at that point? Turns out the normal vector at that point is actually just the gradient vector. So that means state this clearly. Given a function f of x, y, z, if fab equals to 0, basically saying that a point ABC belongs to the level surface fxy being 0, and suppose that the gradient of f is non-zero, then the tangent plane to the function, to the surface at the point ABC is simply gradient of f ABC multiplied by this guy being 0. So you can see that this formulation is nothing but stating that this is actually the normal vector, right? Because that is basically the equation that I gave you guys in 12.5 in the plane section. And secondly, the normal line is given to be this guy, ABC plus gradient of FEC T, where T belongs to R. And we didn't really define what normal line is, but you can imagine it is simply, I don't want to make a formal definition here because it is quite intuitive. If you have a surface, then a normal line is simply that if this is a tangent plane, normal line is just this line, which is perpendicular to every tangent vector on the tangent plane. Okay, so if you have a ball, the tangent vector is simply something like this, Okay, sorry, the normal vector. So again, this is really not a big deal. These two things are stating the same thing, which is that the gradient of f at the point ABC is normal vector at the point ABC, right? So yeah, let's go to the proof. The proof is also not that difficult. It almost follows from implicit function theorem. So yeah, as I mentioned above, that the 2.1 and 2 is simply stating that the gradient vector has to be a normal vector to the surface at the point ABC. So now, given the gradient of f being non-zero, we have this, yeah. Actually, sorry, I should be consistent. Given this being non-zero, then we can assume that one of those is non-zero, right? You can do the algorithm, you can do the proof for fx and fy. In this case, I assume fz is non-zero. So by the implicit function theorem, z is locally solvable, right? As we have mentioned in 14.5, the trivial section. And also we have that the differentiation of z as a function of x and y with respect to x is minus fx divided by fz, and the differentiation of z with respect to y is minus fy divided by fz. Okay, so how does that help us? So we know that as a function, this means that the change of rate with z respect to x is this guy where y is not moving, right? That means that this is a tangent vector, 1, 0, and minus this guy. Okay, that corresponds to the sense that if the slope of a two-variable linear equation, which is something like y equals mx plus b, is m, that means that if you move one unit along the x direction, you get m unit along the y direction. So 1, m will be the tangent vector, right? Or the direction vector of the line. Similarly, for v, you have 0, 1, you are moving y, right? And now the differentiation is fy divided by fz with a minus sign. So these are tangent vectors, means that a normal vector can be given by the cross product of these two guys. These two guys here. And now if you do things very carefully, for the x coordinate, you have this guy, which is plus fx divided by fz. For the y coordinate, you have minus this guy, which is fy divided by fz. For the z component, you have simply 1. So you can see that this is actually just parallel to our gradient of fabc, right? Because you can just multiply both sides by this constant. And then you'll get fx, fy, fz, right? So that sort of proves our proposition, which is stating that the gradient vector is actually exactly the normal vector of the surface at the point ABC. Right, so let us go back to the proposition. Again, the proof is not important. The important thing is that you know how to apply this proposition. So whenever we help trying to let you guys find a tangent plane or a normal line, you can apply this kind of formulas, okay? This is one of the generalization of the formula for tangent plane at the point for a function graph. So recall that if we have a function graph, z equals to fxy, then the plane equation is given by something like this, right? fabc plus fxab, x minus a, plus fyab, y minus b, right? So this is the tangent plane equation for a function graph, a particular type of surface. But in this case, we actually generalize this kind of concept because you can rewrite this in fxyz equal to 0, where fxyz can be chosen to be something like fxy minus z, right? So this is a more general theorem that states that each kind of this level surface has a tangent plane with the equation given by this very nice formula. Okay. All right, so having that kind of idea in mind, let us do some exercise. First of all, I want you guys to find a normal line of the paraboloid z equals to x squared plus y squared. So it is called a paraboloid because it looks like this. It's a ball, and each section is a paraboloid. And we want to ask at the point 1, 1, 2, there is a normal line, right? And want to ask whether that normal line intersects the parabola another time, and what is that point? So first of all, let us find the normal line. And we already have the point, right? So the point is to, so it's confusing. So the idea is to find the normal vector. So the normal vector is basically, as mentioned before, the gradient vector. So the gradient of f, x, y, z is simply 2x, 2y, and minus 1. Plugging the corresponding point, you get 2, 2 minus 1. So this will be the normal vector. And then this will be the line equation, okay? Starting from 1, 1, 2, going along the direction, 2, 2 minus 1 for every t. So to solve another point, you simply plug this equation into this paraboloid, which you get 1 plus 2t squared plus 1 plus 2t squared minus z, which is 2 minus t. And then you get t equal to 0 or minus 9 over 8. Where you can see that t equal to 0 actually is just 1, 1, 2. So that is basically what the problem is saying. 1, 1, 2 is on the surface, right? And this will simply be another point. So you plug the number inside the t back, and we get the actual point on the surface and on the normal line. And it is rather obvious that there will be two intersections because you can see that if you have a parabola like this, then you go through one, and there's something better. Okay, anyway, like this. And if you go through some normal line like this, then it goes out another way, right? So now we're actually finding this point, which is minus 5 over 4, minus 5 over 4, and 25 over 8. Okay? All right. So done with the normal line, let us find a tangent surface. Let us do a problem about tangent surface, tangent plane. So now we have this function x square root of x plus square root of y plus square root of z equals to square root of c. And the problem wanted to show that for any tangent plane on that surface, the x, y, z intercepts are constant. The sum of x, y, z intercepts are constant. So this is actually a really fascinating conclusion. It is stating that you have different kind of tangent plane along the surface, right? But turns out their intersection with the xy plane, yz plane, and sorry, the x axis, the y axis, and the z axis, those three coordinates add up to the same constant, right? So let us try to do this. Given fxyz being this guy, so we always reinterpret the equation as a level surface of some particular function. In this case, this is 0, right? So the normal line, sorry, the normal vector is given by gradient of fxyz, which is this guy here. So now we can compute the tangent plane of the surface at any point x naught, y naught, z naught being on the tangent, being on the surface. And that is simply the dot product between the gradient vector. I omit the half because it is not really important. It is up to a scaling. And we have x minus x naught, y minus y naught, and z minus z naught, right? So how do we find the x-intercept of this tangent plane? It is simply the intersection between this plane and the x-axis, which is where y and z coordinate are 0. So you plug in y and z being 0, and this is x is what we want to solve. And then it turns out this red x here is simply x naught plus root of x naught y naught plus root of x naught z naught. And this is actually simplified to be, if you factor out the root of x naught, you get root of x naught, root of y naught, and root of z naught, which by definition of the x naught, y naught being on the surface is saying that this is root c, right? So you have root c times root x naught. By a similar argument, you see that the y-intercept and the z-intercept are given by cy naught taking square root and cz naught given square root respectively. So now we add those up, you get cx naught, cy naught, cz naught, which you can factor out the root c. And again, by definition of x naught, y naught, z naught being on the surface, this guy is root c. So root c times root c is c, meaning that whatever x naught, y naught, z naught are, whatever point you are choosing on a tangent on the surface, the x and y and z intercept always sum to the same thing, c. Okay, so that's a kind of a fascinating conclusion. We won't go deep, but this is one of the application of you finding the tangent plane. Okay. All right. So let's go back what we were discussing in this section. So this section is directional differentiation and gradient vector. So first of all, we introduce a directional derivative, which is a generalization of the partial derivative along x and y direction. And then we show that turns out that you can represent the directional differentiation in terms of the gradient, which is just an alignment of each partial derivatives, fx, fy, and possibly fz, fw, all the variables. And that the formula itself is given by the differentiation being the gradient taking dot product with the directional vector. And under that formula, we see that the directional vector is maximized when u is along the direction of the gradient, and the maximal value is the magnitude of the gradient. Whereas the minimum of the directional differentiation is the minus of the magnitude of gradient, and it is along the direction of the opposite direction of the gradient vector. Okay, and then we do several exercises on that, which I also encourage you guys to just look up gradient descent algorithm. There's a bunch of nice video on YouTube. Perhaps I will put one in the canvas. And lastly, we learned that the gradient vector also serves as a normal vector of a free variable function. sorry, let me reverse that. We also learned that the gradient vector is served as a normal vector of the level surface of some three variable function. To be precise, if we consider the surface f of x, y, z being 0, then this will be the corresponding tangent plane at the point ABC to this surface. And similarly, we have the normal line of that point to the surface. Okay. And we have shown two exercises. One is about the normal line, one is about tangent plane. So this is not a really conceptually hard section. There is no really new ideas here. Actually, there are, but it is not really difficult. So the point here is to know how to find your tangent planes of a level surface and know how you find your normal line at a level surface. And obviously, you have to know how to find directional differentiations based on this proposition, this formula. Okay. All right. We will use gradient a lot afterwards, but that will be in chapter 16. So I will see you then. All right. I wish you guys all have a good midterm. I think we will see in another video on Monday, which is on the review. So see you guys.